Well, thank you for coming. My name is Fabian Pease. I'm a retired professor of electrical engineering at Stanford University, and I was lucky enough to have Ali Noje as a graduate student several years ago. And although I'm retired, I still like to think I'm reasonably active. And I wasn't sure quite at what point I should begin the history of this talk. Let's start with the week after Memorial Day. That's the United States Memorial Day, 2014. There was a meeting in Washington, D.C. at a conference that we call the Three Beams Conference. The three beams being electrons, ions, and photons. And he and I were both there. And there was parallel sessions, and I was chairing one, and he went to another session. And there was a talk there on something called the Foldscope, which I'm afraid didn't really excite me, so I probably wouldn't have gone anyhow. But Ali and I had dinner that evening, and he said, this was an extraordinary talk. This fellow, Manu Prakash, gave a talk on a light microscope that he'd now made about 10,000 of. He was making, in the process of making 50,000 of them, for $1 each. And what he was trying to do was to populate developing world clinics with instruments they could afford. And they can afford $1. They can't probably afford a $20,000 Zeiss microscope with all the bells and whistles. And anyhow, in some humid climate, it probably wouldn't last too long anyhow. But so that was his mission. And then I would like to show you a Foldscope, and we have three here. Unfortunately, they're in Professor Noje's office. But all I can say is it looks a bit like this. It looks a bit like an envelope. The critical part is a little glass sphere in here, and you put a slide in here, and you hold up to your eye, and you focus it by twisting this backwards and forwards. And to make it really practical, you can also get a little magnetic clip. That doesn't The $1 does not include the magnetic clip that goes onto your iPhone or some other smartphone, so you can display on the screen. And furthermore, you can also get a little LED thing. It looks a bit like a silicon chip, which is what it is. It clips, well, it's not silicon, it's a 3.5, but we won't go into that. It clips onto the other side, so you have your own illumination. Now, he even claims that with an iPhone, which has the flashlight right next to the camera lens, that it works in reflection. I've never seen it work in reflection yet, so that to me. So it also turned out that Manu Prakash worked in the building next door to me back at Stanford. So it's another case of going across the continent to find out what's going on next door. So as soon as I got back, I got hold of Manu and said, I want to see this. And so he said, well, it's funny, because you're the guy I want to see, because I want to do the same thing with an electron microscope. He said, in particular, scanning electron microscope. And I said, well, you know, other people have tried to make cheap scanning electron microscopes. And the trouble is, the electrons have to go from one end of the column to the other end here, and they need a vacuum. They need a high vacuum, about 10 to the minus 4 millimeters of mercury, or it's about 10 to the minus 7 atmospheres. For that, you need two pumps, one to take it down to about 10 to the minus 2, another one to take it further. And if you want this thing to be easy to use, you don't want to have to plumb it into the running water as an oil diffusion pump does, so you need a turbo pump. And a turbo pump costs typically $5,000 straight off the top, so goodbye to your cheap SEM. But Manu pushed me, which was good, because he said, well, you know, do you really have to have a vacuum if the electrons don't have to go too far? Well, I said, that's a scanning tunneling microscope. How many of you know what a scanning tunneling microscope is? Okay, we've got a few here. Well, let me explain this. All it is you have a metal point that comes up to another conducting surface, and there's a tunneling current that goes between the two metals if you can hold that at about 1 nanometer gap. which isn't easy. 1 nanometer is pretty small. But how you do it is you have a feedback system. And then you scan this, and you record the tunneling current, and you can get actually pictures of atoms this way. And that's how Binnigan Rohr at IBM got the Nobel Prize for the scanning tunneling microscope. Actually, it was a 3-way prize, 2 at IBM for the scanning tunneling microscope, and Ernst Ruska, who by then was 80, who got it for the original electron microscope. So anyhow, scanning tunneling microscope, as you can imagine, is a very tricky thing to use, and it's only useful if your surface is pristine clean, which isn't usually the case in developing world clinics or anywhere else for that matter. So I said scanning tunneling microscopes are a hopeless thing to use. I've used them, they're very difficult to use. But he kept pushing me, and so in the end I agreed we would look at it. And the other thing he said was that the Ebola virus was first identified in a scanning electron microscope. Now, I'm not sure that's actually taken in a scanning electron microscope. It is an electron micrograph. So maybe at this time we should sort of take a little bit of a tutorial and explain the difference between a scanning electron microscope and a regular, or transmission, as we now call it, electron microscope. So on the right is what we call now the TEM. In the old days, when I started 50 years ago, 55 now, this was simply called the electron microscope, because the scanning one didn't exist to all intents and purposes. And this is the analog of a light microscope. You have a large source, it illuminates a large angle, a large area on the sample, and each sort of pixel on the sample, each point, generates its own focusable information, which usually is just transmitted light, or it could be fluorescence, and magnifies it and puts it to an image here. So the information you get from here has to be focused. Now, you can do this with an electron microscope, providing the sample is very, very thin, 10 to 100 nanometers perhaps. And so that kind of restricts its use. It's very useful for lots of things. You can get super high resolution. By 1960, we were seeing individual lattice planes in a TEM. The scanning electron microscope, a bit different. You have a small source, and you just create a fine pencil of electrons. In the STM, it was a mechanical pencil, and you scan across here with a scan generator, and the scan generator feeds both the deflection of the beam and some image system, and you collect some signal, which doesn't have to be focused, because now you've divided up this into time, not just space. And so you can collect X-rays, absorbed current, and usually it's secondary electron current, and that gives you the displayed image. So this is simple, high resolution, but it needs a very thin sample. This is slow, but you get a much richer information, and it doesn't in fact have as high a resolution in reflection as this has in transmission. So in 1960, well, let's go back even further. The first scanning electron microscope, there can be arguments about this, but this is my pitch, was in fact at the RCA labs in Princeton, 1942. And this was the diagram of what they made, and it looks rather similar to the previous diagram. Electron gun, usually a rather large source, which you have to have a series of lenses to reduce it to a pencil that you scan with a deflection generator, which also scans your CRT, your viewing tube. And then you collect something from the collector with a signal amplifier that modulates it as you scan, so you build up the picture, as in the TV system. And you need your diffusion pump, and there needs to be another rotary pump out here, because the diffusion pump will only take it the last few orders of magnitude, as we talked about a little earlier. So that's the sort of basic principle. But if you actually have to build one of these things, and we're not going to read all these things, but here is the electron beam column now firing upwards. You've got a gun here, which gives you a source of about 50 microns. Everyone's sort of familiar. A micron is a thousandth of a millimeter, and a nanometer is a millionth of a millimeter. So for those of you, and To give you an idea, hair is about 75 microns across. So the source of electrons here is about the diameter of your hair, of one hair. Then you have a series of lenses, that's what these trios of electrodes are, and the sample can be scanned either electrically or mechanically, and the secondary electron signal was reaccelerated back to a phosphor here, a photomultiplier, and then all this gave you your image down here. So it's quite a complicated system, but they built one. This is a picture of it. That's where the electron column is. The vacuum system's down here. This is a very stable high voltage system, gives about 50 kilovolts, and all the rest, the scanning display, lens supplies, and all the rest of it are there. So it's quite a complicated beast. Rather more complicated than a simple TEM, which RCA was already making and selling. And they did get an image. This is what they say, magnification 6,000 times. Now this is a problem. When you say 6,000 times, that refers to when your image size is about 100 millimeters. Obviously all we have to do is to turn a knob, we can change the magnification. So it's much better to have a scale bar. This is something that I emphasize to my students, the freshman class that I run. I said, if you show me a micrograph that doesn't have a scale bar on it, I will get very upset. But there's no use me getting upset with the RCA group in 42. And indeed, you'll see later that even I have to eat crow. But it's not a very good picture. It has a resolution maybe of 100 nanometers, a bit better than a light microscope. Doesn't tell you very much. It's etched brass, but I wouldn't have noticed that was etched brass if they didn't tell me. So they abandoned it. And, you know, the war was just getting going, and they were making lots of money on the TEM, which was simpler, had better resolution. Because the big deal about the electron microscope is it had better resolution than a light microscope, and that was all we were interested in, really. So let's now go to sort of the third beginning, which is 1960. If you take Moore's law and plot it backwards to 1 transistor per chip, you get to 1960. It was also the year that I started my research work, and I decided to attack the problem of resolution in the scanning electron microscope. I was about the 8th student on this. The project overall started in the late 40s under Charles Oatley, who became my professor. And he and his students had built a series of microscopes, and mine was in fact the 5th one. And again, it's not too different from the RCA system. You had a source of electrons. These are 3 lenses, sample at the top. This is, you scanned the whole thing electrically with these 2 coils here. The collector was a rather different arrangement than he had. This is called a scintillator photomultiplier, sometimes called the Everhart Thornleigh detector after the 2 students who devised it before I came along. Now, this looks pretty complicated, and you can see there's a whole lot of stuff here, and not even shown as 2 more racks of power supplies, which I had to keep well away from the electron beam column because the transformers put out magnetic fields that wobble the beam, and that's bad. But the only important part of the microscope is right up here. It's this final lens that some people call the objective lens that forms the final electron probe on the sample right on the end of that dark thing there. So all this is because the source size is rather large. So we have here a source, again about 50 microns diameter, putting out maybe half a milliamp. And by the time you've demagnified it, you've thrown away just about all the current, you wind up with a few picoamps right here. So in other words, you've lost about 10 to the 8th parts out of 10 to the 8th parts plus 1 of your current. So you're very wasteful of current. All right, so that was 1963. About a year and a half later, and this was brought to my attention by Professor Noget, because December 65 was when they introduced the first commercial scanning electron microscope. And although the electrons shoot downwards rather than up, this really wasn't too different from the one I'd built. Except actually it didn't give as good a resolution, but that's a different story. But you can see that here's the display, all the controls here. The vacuum stuff's underneath here, and not shown are two big racks of power supplies off to the side for the same reason that I had them. Now, I was interested in resolution at the time, and I'm happy to say that I did get the 10 nanometer resolution that was the target. Otherwise, I wouldn't be here talking to you. But then I went to Berkeley, and we didn't have such a good SEM. Now, in fact, I was working with Everhart, of the Everhart Thornleigh detector, and he's had built this machine, and I decided to see if we could look at biological applications with it. Now, I worked with a fellow called Tom Hayes in medical physics, and he made some very obvious comments to me that I hadn't even realized, which is that here's a TEM, it has great resolution, this is an image of a grid. And you can see it's a grid, black bars and all the rest of it. Here's a scanning electron micrograph, the same grid. Now, you can see right away, that's a woven grid, isn't it? To try to determine that's woven from a TEM would be a very tricky thing to do. So he said, the great thing is, it gives you a sort of three-dimensional picture that looks just like our regular experience. For those of you who are really eagle-eyed, you might notice there's a very thin film of stuff here with a few white spots in various places. Those are actually cells from the insides of Tom Hayes' mouth that he stuck on here. And so we looked at that, but that's, again, isn't part of what... The point I'm trying to make out is the SEM is a very useful thing. And this is the point that Manu Prakash was making to me, was that it's such a useful tool. One of the other nice things about it is that it needs no specimen preparation. So one of the people that Tom Hayes introduced me to was a fellow called Larry McDonald. He worked in the radiation lab, which we now call the Lawrence Berkeley lab. And he was interested in radiation effects on living samples. So he picked the flower beetle. So he produced the pupa of a flower beetle and said, could we look at it in the SEM? So I took a piece of cooking foil and just sort of bent it into a trough shape, stuck it in the SEM and looked at it. And, you can see this is a huge field of view because this thing's a few millimeters long. The other nice thing is that if you didn't leave it in for longer than 30 minutes, it survived and went on to become an adult, this guy here. And I know Cassandra, who made the poster that advertised this talk, had a beautiful picture of a fly's eye. I don't have the poster here. But this is a picture that we took back in 1966. And for those of you who are aspiring tenured professors, let me give you another digression here. I was an acting assistant professor, step one. I don't think you can be a lower level of faculty employee. Maybe you can, but I didn't. Certainly, my tenure case was going nowhere because the chairman was interested in system theory, and I was about as far from system theory as you can be in a EE department. But this picture made it to the cover of a very high-impact journal, the San Francisco Chronicle, with the headline, Berkeley's Marvelous Microscope. And after that, I couldn't put a foot wrong. So those of you who are looking for tenure, just remember, it's not just the erudite journals that you publish in. If you can bring your department good publicity, that's a much easier alternative, I think. So I digress a little. Let's keep going, because otherwise you'll miss, we'll get thrown out of here or something. Now, the standards of electrons, SEM, sort of stayed the same for about, I don't know, 20 or 30 years. This was taken last week in my lab. And you can see there's the column, the electron beam generated at the top. This is a high voltage cable with 3 lenses, sample chamber down here. I took it from the back, so you can't see the display, but this is the back of the display. In fact, that's just the end of the cathode ray tube. And there's lots of electronics here, and there's a vacuum pump there, another vacuum pump down here. This thing not only has to have 220 volts 3-phase, it has to have compressed air to run the valves, as well as running water for the diffusion pump. So it's okay for a lab that we have here, not too good for a clinic in Burkina Faso, for example. So that dates from maybe 20, 25 years ago. But about 10 years ago, people started to realize that if you wanted an SEM that was useful to a lot of people, you better make it A, less expensive, and B, easy to use. So Hitachi came out with this one. This was taken, and I've got one of these in my lab. This was in fact photographed just taken last week. It's about the size of a tabletop refrigerator. All you have to do is to plug it into the wall outlet and switch it on there and turn on the host computer. And that's a simply old, in fact the difficulty is it runs XP, so you have to find an old computer that isn't hooked up to the internet. And to change this sample, you simply turn that switch, wait for it to come up to air, pull that out, put your sample in, put it back, press the go button, you're in business again. Dead easy to use, no ritual you have to go through. It does, however, even 10 years ago, cost $60,000, which was a lot cheaper than a regular SEM then, which was costing about $150,000, but still out of sight for most clinics. Now, I did have a colleague who said he wanted to make one for $10,000, and he looked very closely at this one and said, you know, Hitachi have done a pretty good job. I don't think I could really do better. So that was what was at the back of my mind when Manu Prakash said, you know, what can you do? These are just 4 pictures taken with that TM1000 we just saw, and it illustrates a point, another very obvious point that was made to me by a freshman about 5 years ago. He said the great thing about the SEM is the huge range of magnifications. Here's a complete screw, that's 4mm scale bar, and you can zoom in so you can look at that black patch there and you see this guy here. Then if you look down here, you see that patch there, and that magnifies to this guy here, which magnifies to that. And that's 2,000 times on the screen, so that's 30 micron marker there. You can do 10 times better than that on a regular SEM anyhow. Hitachi actually don't call this an SEM, they call it an intermediate electron microscope, because it's sort of intermediate between a regular SEM. But nonetheless, this is what it can do. Now, I've shown you then sort of how the things stand, and now what I really want to do is to invite you to help us realize Manu Prakash's dream. He pushed me, and he said, look, do we really have to have such a good vacuum? Well, I dug out that RCA work again. It's a textbook written in 1945, and then they had this picture of a diagram of the mean free path for electrons up here in centimeters, so that's 1 centimeter here, versus pressure. So here's 10 to the minus 4, which is the highest pressure which a regular electron microscope scanning or otherwise could work at down here. Atmospheric pressure is nudging 10 to the 3, so it's somewhere around here. And as I say, a cheap pump can certainly get you down to about 10 to the minus 2, which gets you a centimeter. Well, how much do you need? Now, that Hitachi microscope I showed you, in fact, has a very different detection system from the Everhart Thornleigh one. And let's just sort of show you then. Having sort of demolished my need a vacuum pump argument, I then had to get to work. And this is why I want you to help. He said, can we have a very short focal length? Now, in the Hitachi that I just showed you, the detector is what we call a quadrant. This is simply a p-n junction in a silicon wafer. So the electrons come back onto that, and that's how you detect them. So you take the signal from these diodes. It's really a solar cell divided into 4. In fact, in the Hitachi, they connect them all together, which I don't think is the right thing to do, but you can separate them. Now the vacuum. So the idea is you do have a vacuum. So we start with a source here, and I'm trying to make a source, or we are trying to make a source, which is why I'm in Vancouver, as a matter of fact, that's about ½ a micron. Then if we can demagnify that by about 20 times, we can get down to a useful beam diameter here. So I'm looking for, and I'm by those of you who know optics realize I got that ray diagram the wrong way around, but so the idea is then you've got vacuum to here, you have a window, a very thin material like silicon nitride, but it only has to span about a micron diameter. So it's a very small and very thin window, and you bring the electrons out through the window onto the sample that may be a fraction of a millimeter away from this detector, which you remember is sort of facing downwards on the sample that's at the top here. So this thing now can be a sealed off tube. If you go downstairs, there is an exhibit showing all the vacuum tubes, not all the vacuum, they're showing a nice selection of vacuum tubes, and vacuum tubes would sell for a few dollars. So we could make a vacuum tube, of course you've got to make lots of them, to make it cheap, and seal the thing off, and we have a source at the top, as indeed a vacuum tube does, then this could be really cheap. And no vacuum pump up there. You might need to do something down here, but that would be a very cheap one. And in fact, if it's atmospheric pressure, if you can put it within a micron, you're okay. The magnetic lens does its focusing around here, so the blue is a magnetic circuit for those who know magnetic lenses. So this is what we're trying to build. And there are a number of critical challenges that we have to do. Now, we're not the first people to make what they call an atmospheric SEM, so there is a precedent. This, in fact, is now available commercially by JOL, and the idea here is that the electron beam comes up, and the sample, there's your window, and on top of the window you simply have your liquid, say it might be some water solution with your cells right up against the window there. So the electron beams go through the window and they immediately hit your sample. They have this kind of quadrant detector we talked about before. So that's a picture of the window there. Here you see you just have a Petri dish with your stuff in. This has got to be a Petri dish with a very thin bottom. And indeed, they have been getting pictures on this machine. By any chance, does anyone have one of these here? I've never seen one. Oh, what a shame. I was hoping someone could tell us all about it. So this is a bit of a cheat of a sample, but there's the arrangement. They put some little gold particles here. Now, gold, you see, is really cheating because you get a beautifully high reflection backscatter coefficient. Backscatter electrons are those that go in at high energy and come out. So they're the reflected primary electrons. There are also low energy, a few EV secondaries. They're not going to go anywhere here. So we're going to forget the low energy secondaries for now and just work on the backscatter, which indeed is what the Hitachi microscope that I showed you uses, and uses very effectively. So this shows some of the two different voltages, 20 kV, 30 kV. This is a 100 nanometer scale bar, so this is certainly far better than any light microscope will do. At least we won't count some of the new gee whiz things that won the Nobel Prize last year, but the kind that you and I use. And it's called an Asm Atmospheric Sem. So although it doesn't go, now they made the nitride window, they could make it 100 nanometers because they didn't worry at what angle the electrons emerged. We won't have that advantage because we're trying to put some separation between the sample and the window. On the other hand, they're scanning across the window, so they need to cover a larger field of view, whereas we're going to do mechanical scanning so that we can leave the electron beam stationary and just scan. So yes, so the idea of bringing your beam out into atmosphere isn't original with us, and I'm very happy that we have a precedent because it makes our case a little bit easier to sell. So these are sort of what I think are the critically expensive parts that we have to work on. There is the gun, which includes the source. I mentioned we don't want a 50 micron source because then you need a series of lenses. We just want to get away with one lens with, say, a demagnification of 20 times. So this is, in fact, what I'm working on with Professor Noger's group, who's represented in the audience here. And I'll say a little bit about that in a moment. The other thing we needed before was a very stable power supply, 10 parts per million per minute. And with a conventional gun, that it has to deliver up to a milliamp. Maybe you get away with a quarter of a milliamp, but because remember, you had to throw away so much current with a conventional system. But if you get away with a small source, then all it has to deliver is 1 nanoamp. Because remember, we can use maybe 1 to 10 picoamps to build the picture up at the sample. So if we only throw away 100-fold, or maybe 400-fold, then 1 nanoamp. And that has two advantages. One, it's less expensive, and B, it's not lethal. 1 milliamp, 50 kp, I wouldn't like to test it, but I think that's lethal. But 1 nanoamp, you won't even feel. Just last week, they gave me some treatment here, and they were putting 100 milliamps into me. And yeah, I could feel it, but I'm talking about 100 million times less. Vacuum pumps, how we're going to solve that problem is going to avoid them. We're going to get the sealed off tube. Now, there's apparently a place here in Richmond. You see, making vacuum tubes is, if not dead, it's a dying art. But Professor Noger and his group know a fellow in Richmond here who knows how to do it. So that's another reason I'm here. The final lens, stable to 5 parts per million per minute current supply. Although it's twice the stability needed there, it's a much easier thing to do. But in fact, originally, I had in mind using what we call a surface resonant plasmonic source. This was some work that I did in conjunction with Professor Hessling's group. Actually, this was before we'd even got around to thinking about the cheap SEM, but we did want a 20 nanometer electron beam source. I'm going to try to get around it. I'm suggesting we get around it using permanent magnets as the main magnetomotive force to generate the magnetic field for focusing the electrons, and simply use an electromagnetic, just a coil, to finally focus. And it's clearly much less expensive to make a low current supply than a high current. The detector, I think I've talked about that. And there's the window as well, so we're looking into that. But there's the scanning system, and I think a mechanical scanning system. I was playing a bit with some designs this morning, but this is something that I don't know much about, and that's something that we really need help on. And the final thing is the display. How are we actually going to display the image? The scanning system, by the way, the mechanical system, normally you think of a scanning system to build up a picture as being a very nice linear uniform scan to build it up. But in these days of free computation, if you think back to the original diagram of the SEM, as long as you know the address of where the beam is on the sample, and you can measure the signal coming off, even if it's not uniform, you can use some free computation, which is what we have now, to build up a good-looking image. So we should exploit free computation. And then finally the display. Now that I'm looking to other people, such as yourselves in particular, to look into. I don't have it on me, but I want the display to be on, I think, a smartphone, as indeed Manu Prakash's Foldscope is too. So clearly I need people who are less than a third of my age to work on that aspect of it. So what are we doing here? Now, unfortunately, the source is something I've talked about, and the idea being that this is 20 nanometers here, and this aluminum structure, well, this is a C aperture that's been etched out of 40 nanometer thick aluminum with a scanning helium ion microscope. Has anyone ever used one of these scanning helium ion microscopes? I never have myself, but Hessling's people went after. It's an extraordinary tool. Bear in mind that this structure, that's 20 nanometers, is etched in twice that thickness. So it's really an amazing structure to make it that small. But if you shine a laser beam on here, the field will be concentrated at the end of this little proboscis here, and so you'll pull off. So these are the photoelectron currents that we were pulling off this thing. They're claiming they're getting down to 20 nanometers. I won't go into the details, but it's certainly small enough for RSEM. So that's one approach. Now, I don't know how long-lived these are and all the rest of it. But the other exciting thing was that really got a lot of us very intrigued was work done right here by Professor Noget. He, for his PhD, was interested in electron emission from carbon nanotubes. And he retained that interest after he got here. And he was initially interested in photoelectron emission from carbon nanotubes. And members of this group can correct me if I'm wrong, but my understanding was that to get photo emission, he needed a blue laser. But to get a blue laser, he had to agree to buy a green one too. And one day they shone the green light at the carbon nanotubes, expecting to get no electrons, but in fact, they got electrons. And what they discovered was the thing was anomalously heating up. And so they were getting thermionic emission from the carbon nanotube forest. So this is the bias voltage, that's the current, and you see they're getting up here to, that is a 10 to the minus 6, I believe. Is that, anyone here, any of the original people? So there were, and it's stable, at least reasonably stable, and certainly has prospects of being much more stable than the photoelectron beam that we saw earlier. So we're working on this as we talk to see if we can get this whole thing to be very small, and we need about 1 amp per square centimeter, which is about what you can get from most thermionic emitters. So the experiment that we're sort of setting up right now looks something like this. I think I've lost my laser pointer. Yeah. Light, the green turquoise stuff coming in from the top right, hits the carbon nanotube. The thing works in reflection at the moment, and we're trying then to pull the blue electrons off onto a phosphor, and we'll put a 2000 mesh grid up there, so we will see a point projection image of the mesh here. Do we have a picture yet, by the way? I guess we don't. I was hoping in the last 20 minutes we might have. Well, I see Mike at the back shaking his head. What a shame. I'd love to have shown that just to finish up. I knew we should have had the talk on Thursday. Then with a point projection, you see, you'll get a picture of the mesh, and it will be blurred according to the size of the source. So the size, you know the bar is, say, 5 microns, and so that gives you a scale bar, and you look at the extent of the blur, that's the size of your source. So if it's sort of blurred by 20% on either side, you know you've got a source size of about a micron, which is sort of what we're shooting for. So that's what we're doing at the moment. So we've got lots and lots of challenges. We're trying to do this for a sale price, well, no, I should say a building price of $150 each when we're in large-scale production, which is a long way off yet. But the idea of being able, the thing might be about this big, and oh, there you got a picture of the poster there. Yeah, there's the picture of the fly's eye. So we can get a picture like that for $150 machine. I think it's a very exciting project, and if you've got ideas on the mechanical scanning, on the high voltage set, we've already got one alternative set. Oh, I didn't tell you about the high voltage set. We have a fellow called Yi Chui in the material science department at Stanford. He's an expert in batteries. And I described the problem, And at one point I had in mind you'd have a huge sort of tube, Teflon tube, and I'd drop watch batteries into it, 10,000 of them, to get 30,000 volts across the end. And of course, that wasn't a very good idea, but it was enough to get him interested. We don't have to do that, he said. If you only want a nanoamp, you work out how many milliamp hours a nanoamp, how many hours it'll give you. It's about 3 years, I think. So he said we could print these batteries at such low capacity, a whole series of them, in about a foot-long insulator, so that you'll get 50,000 volts from one end to the other. You won't be able to pull much current out of it, but you only want a nanoamp. And I even thought, well, maybe we could even print it on the inside of that glass vacuum tube we had, but that's going a little far. So that's one idea. And then we have another one that came from locally. The fellow was suggesting that we could, in fact, make a little high voltage set with a feedback loop to stabilize it. And it's possible. I'm open to all suggestions. Mechanical scanning, yes. If anyone's here an expert in how to make mechanical scanners cheaply, I approached one outfit that made them, and they described this wonderful system with piezoelectric scanners and all the rest of it. And I said, well, you know, how much does it cost? They said, well, the starting price is $20,000. I budgeted 50. So that's another thing. And display. If you can work out some way in which we could take the output, I can know how to go through a video amplifier, I can do all that. It's when you get to the interface with the smartphone that my eyes go glassy and I scream for help. So yes, I want your ideas. I'm not expecting you. If you have some right now, I'd love to hear them. But go away and think about it and get in touch with me. Did I give my email here? No. No. Well, you know my name. It's spelled like please without the L, at stanford.edu. Remember that? Shouldn't be too difficult. And if you do forget it, talk to Professor Noget. He will get in touch with me. And he's part of the team, so he'd be very happy to discuss this with you. So please go and think about this. We really need your help. We need everyone's help we can get. We're not trying to corner the market or anything. We want to get this thing to fly. You've been very patient. I'd be happy to answer any questions if you have some. And if not, thanks so much. Any questions? Yes?
With the mechanical scanner, what resolution are you looking for?
Oh, good question. What sort of, yeah, I'm looking for, I think, a millimeter maximum. Yeah, millimeter maximum field, minimum 10 microns, so that's 100 to 1. Speed, I was thinking about this morning. I think if we had the fast scan at 60 hertz, and the slow scan, maybe it would take 10 seconds. So it'd take 10 seconds to build up a picture. So I was thinking about a vibrating cantilever for the 60 hertz, and then maybe a screw drive for the 10-second scan. What do you think?
Yeah, first thing for 60 hertz comes to mind is a piezoelectric that costs about.
Yeah, how far do piezoelectric scanners scan? That's what.
Because they go way beyond 60 hertz.
No, how far can they scan? Can they go? Usually, you see these scanning and tunneling microscopes and the atomic force microscopes. They don't scan as much as a millimeter, I don't think. But it's a nice thing. They have that sort of pillar which scans in both directions, and it's a handy thing. But I don't think I really want to be able to scan a large area because that's one of the attractions of the SEM, I think. Yes.
I'm a biologist.
Good.
So I came to learn more about the physics behind the scopes we use. But the one thing that I thought all these years in a scanning or an EM for that matter was that there had to be no barrier between the beam and the sample. But you're designing something that's going to be a sealed tube.
But the sample is outside the sealed tube.
Yeah. So I don't understand how that would work.
Well, because you have a thin window that the electrons go straight through.
So it's so thin that it's
yes.
retaining the vacuum. It's actual physical barrier.
Yes. Wow. Well, it's in fact not unlike the sample of a transmission electron microscope, where the electrons have to go straight through without serious scattering. And even in a TEM, they actually do make little water vapor cells, don't they, for biological material?
I didn't know that.
Yeah. So good point, though. Yeah. I think we'll see what we can get away with.
And that would have to be cheap enough that it would be replaceable, because it would be potentially fragile.
Well, how often did you have to replace the vacuum? No, you're not old enough to remember vacuum tube radios. When I first came to North America, which is now 50 years ago, at the entrance to each supermarket, there was a vacuum tube tester. So if your tubes were suspect, you simply plug them in. There was a whole array of different sockets for them to go in, and you could check them out. But they were clearly got taken out a long time ago. Yeah. But no, I've still got vacuumed. I keep them for historical purposes, and I showed one to an undergraduate thinking he'd be wowed by it, and said, "Oh yeah, I got 2 of those for the amplifier of my electric guitar." So, yeah, you actually raised a point, which I meant to make and didn't. The last television I bought was a color tube television, $150. Now, 1965, when they introduced the SEM, was also, in fact, the year Gordon Moore enunciated his famous law. But SEMs didn't get less expensive, they got more expensive, unlike computers. Color television was just coming in then. You spent, I think, several $1,000s, 1964, $5, for a color TV. It really wasn't very good. Whereas, as I say, 30 years later, I bought one for $150. Unfortunately, it was an analog set, and we're all digital now in the United States, so I had to throw it away. But a color TV tube is a lot more complicated than that thing. I mean, it's got 3 sources in it, each which are individually modulated, huge area scanning, and then you've got to sort of separate out the 3 color beams when they get to the target over a huge area. It's a remarkable piece of engineering. The whole thing, including all the circuitry, was $150. So if they can do it, we should be able to do it. Yeah. Anything else? Anyone else got to it? Yes.
Where does the detector sit? Is this on the outside or is this on the inside?
They're on the outside, yes, but they're close.
Oh, very close.
Yes.
Because the secondary electrons will have...
They won't get there.
Yeah. Oh,
The best they could do would be to generate some fluorescence in the air around them, and the photodetectors would see that. And I think what we might see is, in fact, not full atmospheric pressure, but some inexpensively pumped down area around there with a simple rotary pump, because that will increase your mean free path. So if we can get it up to, say, 1 millimeter, that would be terrific, wouldn't it?
Yeah. So you would be detecting backscatter?
Yes, as indeed the Hitachi SEM does that I showed you, right?
So that sample wouldn't charge up with the
Oh, no.
secondary electrons?
Well, the nice thing about having a lousy vacuum is that there's enough ions and stuff around in the air to discharge the sample. That's one of the advantages, in fact, of that Hitachi SEM. In the chamber, it has a rather crummy vacuum. The gun does need a good vacuum. It needs a full 10 to minus 4. If it's tungsten, if it's anything else, it needs to be a good deal better than that. I'm actually hoping that with the sealed off tube, we might have a much greater choice of thermionic emitter materials. After all, a vacuum tube uses barium oxide and stuff like that. And you put one of those cathodes in what we call a demountably pumped system, it will die in no time, which is why they're not used in electron microscopes. Well, lanthanum boride is sort of a compromise. And field emission, if it was reliable and easy to use, would be ideal. But field emission is a brute to use, and it needs a super high vacuum and a little bit of ion damage and the beam goes off to one side or dies. So some of you may have used a field emission SEM. When they're working, they're really beautiful things to use, but it takes some doing to get them to work properly. Have you used a field emission SEM in your lab?
Once or twice.
Who made it? Is it a Hitachi one?
Hitachi.
Yeah. Is it an easy to use one?
I didn't find it so bad,
Okay.
but then I was
But then you're skilled.
still by no means.
Yeah. Yeah.
This is a completely naive question, but instead of moving the sample, could you use some kind of micromirrors-like technology to help with some kind of deflection that's non-magnetic?
Well, you've got to move the beam. And if you have to move the beam, then you'll need a larger window holding off atmospheric pressure. So my feeling was use a stationary beam. But I don't know enough about these vacuum windows, but that's certainly a possibility. And then you could use the electronic scanning, because you could put coils outside.
Electronic scanning has a speed advantage, right?
Where are we? One more. Yeah, you could put the magnetic lens, most of it could be down here, and you could put scanning coils outside there. And the eagle eye, if there's any electron microscopists around, you might say, well, where's the stigmata? And I haven't put one in. Partly because I'm hopeful that with a vacuum sealed system, it will be very stable, so any astigmatism correction only has to be done once, and you can do that simply by pushing a sort of screw through here to try to make the magnetic field compensate for any otherwise asymmetry. In other words, if you correct for astigmatism, it's done by, astigmatism is caused by lack of rotational symmetry, as it is indeed in your eye, and you correct it by trying to put in a compensating asymmetry. And there are various ways you can do it. You could even just simply offset the lens a little bit. I make it 5 to 4. You have one question?
Yes.
Go ahead.
Wouldn't you have to worry about X-ray emission? Because you have
Oh, very good question. Yeah. What about X-ray imaging? Well, a regular SEM has the same issue. So as long as you have enough metal around, you should be all right. I said 50,000. I should have picked 40,000. Usually the irregular metal is fine for 40,000 volts. It also makes the arithmetic easier because V often appears under a square root. It's much easier to square root 40,000 than 50,000. But if you want something to work at 40,000, you better engineer it for 50,000, as you're going to find out. Do you have X-ray problems with your microscope?
I don't know.
You haven't checked, yeah. Well, I do know that, you know, if we go above 40 kV, then that counter starts to click. So I keep everything I like to keep below 40 kV.
I assume that it's all shielded nicely.
Yeah.
We don't normally go that high on an SEM. So.
Yeah, a TEM, of course, is different. Now you do have to worry, and that glass is leaded, I know. And the fellow who took over some gear in my lab who's working at 100 kV, and he sort of built a lead tower around the thing. And, I hope we don't get an earthquake soon. But okay, I'd be happy to sort of meet informally with you. And again, Pease at Stanford.edu. If you have any suggestions or see any awful drawbacks as to why it can't be done, we've got to get this thing to fly, and it's got to be done soon because I'm moving on. Thanks very much indeed.